Hi class, welcome to the next video in the pre-calculus series. Today we're going to be going over equations. So we're going to be talking about equations in general, some general ideas for solving equations, some sort of like a big picture-esque type of things rather than like, oh, when you see this, you do this kind of method that you learn in an algebra class, right? So it'll be a little bit more conceptual. We'll have some good examples to go over. It should be a relatively short video compared with the first couple. Again, make sure you have something to write with and something to write on so you have a good set of notes to go along with the lecture notes that are provided, right? So, first we're going to start off by talking about the difference between an expression and an equation, okay? So far, we've really only talked about expressions, right? Algebraic expressions, rational expressions. We haven't really dealt with any equations. The main difference is that one has an equal sign and one does not, okay? The way that we go about solving an equation versus simplifying an expression is completely different. It's related, but it is two completely, literally opposite things, okay? So we'll have a little chart here to go with this. So for an expression, as I said before, there is no equal sign. An equation, you know you have an equation when you have an equal sign. Okay? For an expression, we will simplify the expression to its simplest terms. An equation, we solve. We have one thing on one side of the equal sign, something on the other side of the equal sign, and our goal is to find out how to, what the unknown that we need is in order for the equation to stay balanced, okay? For an expression, our answer is going to be another expression, okay? An expression simplifies down to a simpler expression. An equation gets solved to be a single value, right? X equals 3, x equals 10, y equals 7. Right? We're going to take an equation and we're going to come out with an answer that is a number, okay, a real value. An expression, we are going to simplify it down to a simpler form that's equal to the same expression, okay. For an expression, we want to go through PEMDAS, okay. We're going to start with any parentheses. A lot of students have been telling me that now it's called GEMDAS and not PEMDAS. So GEMDAS means you're looking for any grouping materials, whether they're parentheses or absolute value signs or things of that nature, right? So things that are grouped together, this quantity, right? Then we get rid of any exponents, and then we work on any multiplication or division. These two things are equal because, as I said before, multiplication and division are actually the same thing, right? And then we're looking for any addition or subtraction to process through the expression. Again, because addition and subtraction are really the same thing, they appear equally, as does multiplication and division. So there's kind of a four-step process, right? The grouping, we simplify anything that happens inside of the grouping, and then we apply any exponents, and then any multiplication or division, and then addition and subtraction. When we have an equation, we're actually undoing PEMDAS, okay? We're actually going in the opposite order. We're looking at any addition, subtraction to do, and then any multiplication or division to do, and then we're looking to undo any exponents, and then we can focus on the grouping that's left over after that. So we go in the opposite order, okay? So when I see addition, I'm trying to undo PEMDAS by using subtraction. When I see division, I'm trying to undo PEMDAS and use multiplication. So I'm actually going in the opposite order of PEMDAS, and I'm using the opposite operations that as they appear, okay, which we'll get into deeper. So again, I'm undoing PEMDAS. So I'm going subtraction, addition, still again on the same line, but my goal is to use the opposite operation that I see. So again, I'm looking for any addition or subtraction to undo, right? So if I see some addition, I'm trying to subtract something. Okay, then I move on to the multiplication, and again I'm trying to undo any multiplication or division with its opposite. I'm trying to do any exponents by using the radicals, right? the reciprocal exponents that we have for that, and then I can simplify any of the groupings that are left over at the end. Okay, so I like to sum this up in a single sentence. Okay, for clarification here, I broke that single sentence down into two parts as two separate rules. Okay, actually it's still two rules. So the first one is be equal. Okay, you have to be equal. In an equation, there is an equal sign. So if you are not equal to both sides of the equation, you're not being equal. Okay, so when whatever you do to one side of an equation, you have to do to the other side of the equation, right? If I had two groups of kids and I give all of one of the groups of kids a bunch of cookies and not to the other kids, I'm not being equal anymore, right? I'm unbalanced. Half the kids are going to like me, the other half are going to hate me. I'm not being equal, right? If I gave everybody the same amount of cookies, I'd be great. So that's kind of what's going on here. I want to give out cookies equally across my equation, right? So whatever I do on one side, I have to do on the other side, okay? I have to be equal. I need to isolate my variable, my unknown, by undoing PEMDAS, okay? So we use the order of operations in the opposite order that they appear, right, in order to isolate my variable. So when I say this as a single sentence, I say I have to isolate my variable by undoing PEMDAS and being equal to both sides of the equation. That's how I generally say this to my students as a single sentence. So again, kind of broke this down in two parts for us. Okay. So let's go ahead and solve the following. We will start with this fractional equation, right? 3/2 x plus 2/3 equals 5/4 times x minus 7/6. Now I said this in the last section. Whenever we have fractions and an equal sign, the problem is actually very easy. Okay. So again, I'm a big proponent of clearing denominators. That's the easiest thing to do. So whenever there's a fraction and an equal sign, you can clear out all of the fractions and turn this into an equation that has nothing but whole numbers. Okay. So if you have fractions and equal sign, that's the first thing you want to do. If there is no equal sign, very important, no equal sign and a bunch of fractions, you have to combine like terms. You have to make a common denominator. You have to follow the regular rules of fractions. Okay. You can only clear things out when you have an equation. Okay. So equal sign means equation. I want to know what value of x makes this side equal to this side. Okay. So most of you guys would probably start this off by subtracting the 2/3 and then subtracting this x to the other side. So you have all the x's on one side, all the regular numbers on the other side, and then solving, which is fine, except we don't like fractions. So again, I don't like fractions. So I found the ways around them as best as I could. Like I said before, they were the thing that were hardest for me to grasp, so I did them a lot until they weren't a problem anymore, right? So how I make them not a problem is by getting rid of them. Okay. So what we're going to do is we're going to look at all of the denominators that we have present, 2, 3, 4, and 6, and we want to find the common denominator. Okay. We're not going to make a common denominator, but we're going to find that value. So remember, in algebra, we don't call it the common denominator, we call it the LCM, right? I want to find the LCM. So we talked about this when we were talking about rational expressions. We look at the largest denominator present, and we count multiples of that denominator until all of the other denominators fit into that multiple of the largest one equally. Okay, so again, let's go through this one more time. The first multiple, okay, 6 is my largest denominator, obviously, right? I've been circling it for a while. The first multiple of 6 is 6. 2 goes into 6 evenly. 3 goes into 6 evenly. 4 does not go into 6 evenly. Okay, so since even one of them doesn't work, I have to count up to the next multiple. The next multiple of 6 is 12. 2 goes into 12 evenly. 3 goes into 12 evenly. 4 goes into 12 evenly. And 6 goes into 12 evenly because that's the one I counted by. So my LCM of 2, 3, 4, and 6 is 12. Now some of you would be like, oh, okay, now I'm going to make a common denominator of 12. Multiply this top and bottom by 2, top and bottom by 3, top and bottom by 4, top and bottom by 6. That's way too much work, okay? What we're going to do is we're going to multiply the entire equation, everything, each term. It's always each term. So when I say everything, I don't mean this top, this bottom, this top, this bottom, this top, this bottom, this top, this bottom. No. Each term. This term by 12, this term by 12, this value, this term by 12, and this term by 12. Each individual term, not numerator and denominator both. The whole equation, because then I'm being equal. I multiplied everything by 12, okay? I was equal. Everything on this side of the equation and every term on this side of the equation gets multiplied by 12, right? So again, since we have an equal sign, we can multiply the entire equation by the LCM of the denominators to clear the denominators out. The LCM in this case is 12. So I'm going to do this very slowly for the first example and then not after that. So I'm going to multiply this whole side by 12, this whole side by 12. It's the same as if I take 12 and distribute it into each piece, as I said. So here, what happens is that the 12 and the 2 divide into 6. So this turns into 6 times 3. Okay. 12 into this, 12 and 3 cancel out to a whole number because I know 2, 3, 4, and 6 all go into this evenly. So when I multiply this and it gets divided by each of these denominators, each time I'll end up with a whole number. So 2 goes into 12 gives me 6. 3 goes into 12 gives me 4. The 2 that's on top stays there. Okay, that's one side. Here, 12 and 4 go into 3. The 5x stays the same. Okay, here 12 over 6, because again 12 is a numerator, 6 is a denominator. That will give me 2, so I'll have minus 2. The 7 stays, so minus 2 times 7. No more fractions. Now this is just a regular problem with no more fractions. We don't have to worry about common denominators, adding the fractions, subtracting the fractions, multiplying by reciprocals in order to do our division. We don't have to do anything. We did one step and we no longer have fractions to deal with. Okay, so now obviously I'm going to simplify everything. 18, this will be 8, 15, and 14. And now I can just solve like normal. Again, I'm going to do opposite operations. My goal is to isolate my variable x. So since x is on both sides of the equation, I need to subtract 15 from both sides, right, being equal, or I need to subtract 18 from both sides. I'm still equal because from both sides of the equation, I did the same thing. I either subtracted 15 from both sides, or I subtracted 18x from both sides of the equation. Now, the choice is which one should I do? I always subtract the smaller one, because if you subtract the smaller one, you end up with a positive value, right? If I subtract 18 here, the 18x cancels with the 18x, then I got 15 minus 18x, I end up with a negative. So it's always easier to subtract the smaller side. So if I have to subtract 15x, then that means on this side I will have 3x plus 8 and negative 14. So since I want all the non-variable terms, all the constants on one side and all the variables on the other side, I have to subtract 8 to go over here. So what I'm going to do on both sides of the equation is subtract 15, and on both sides of the equation I'm also going to subtract 8. Okay, so I minus 15 from both sides, that gives me 3. And then I'm going to minus 8 from both sides, and that'll give me a negative 22. Okay, so now to finish solving is easy, right? The only operation that's left is multiplication. So to undo multiplication and isolate x, I divide both sides by 3. And so my answer is negative 22 over 3. So again, I always want exact values in this class. Okay, do not give me some crazy decimal form, right? Don't give me 7.33333333. We talked about rounding and errors and things like that, because again, if I had to use this now for another part in the problem, right, which as we get through this class, our problems become longer and longer and longer, using 7.3 versus 7.3333 versus negative 22 over 3, those are all going to give me different answers in the end, right? Because of rounding error. So again, this is the example. This is the answer that I want. The only time I want a decimal answer is if there's already a decimal present, or if it's an application problem, because negative 22 over 3 feet per second squared, for instance, doesn't make any sense. But 7.33, negative 7.33 feet per second squared would make more sense. So again, application problems, you can put decimal form. For most of this class, I want exact values. Okay. So let's step it up a little bit. So I know no one likes fractions, but they're easy to deal with if you clear the denominators. Okay. So for the next problem that we have, we're going to solve a radical problem. Okay. Remember that the opposite operation of radicals is exponents, right? So remember, radicals are really just exponents, so we'd have to apply the reciprocal exponent value. The problem here is that I have one side is isolated as a radical and the other is not. So when I do this, I need to isolate one of these, which one is already isolated, so there's not much for me to do. Okay. I know you might see this negative 1 and say, oh, let's add the one on the other side. We can do that, but then we'll have the same thing. We'll have a radical plus a constant, and we'll have our radical on the other side isolated, which is fine. That we're just really shifting things around at that point, and nothing's really getting done. So what I want to do is I want to try to undo this square root. So remember, we're trying to isolate x by undoing PEMDAS, right? So the opposite operation of square root is to square things. So I'm going to square this, and I'm going to square this. Okay. Again, remember the common mistake. This is an entire quantity being squared. It's not going to be just x plus 1 minus 1. This does not turn into just x, right? It is this quantity times itself. So there's this special product for that, which is this squared plus 2 times both of these being multiplied times each other plus this term squared, right? So there's a special product here. Please do not make that standard mistake of just squaring this and squaring that and saying that's it, because it's just going to mess you all up, right? So squaring this gives me x plus 1. The sign in the middle is minus, so I'll have a minus 2 times this times that. Okay, and then plus the square of this. And on this side, the square root and this exponent here cancel each other out, because remember, I can write x plus 2 square root as the quantity of x plus 2 raised to the 1/2 power. Okay, so 1/2 times 2 gives me 1. It undoes each other. I end up with x plus 2. So now again, this is a grouping symbol, right? This is an exponent. I want to isolate this. So in order to isolate this, I'm going to try to move everything else to the other side of the equation by using opposite operations. So again, isolate this. So I can combine the 1 plus 1 and get a 2. And then I need to move the x to the other side and that 2 to the other side. So I'll actually end up subtracting x on both sides and subtracting 2 on both sides. So that'll end up with 0 on this side, right? So I'll have the middle term still negative, 2 times square root x plus 1, and nothing left over because the x cancels with the x, and this one is 2 and cancel with that 2, right? So next thing I want to do is, again, I'm trying to isolate this part, the square root term, so I can get rid of the negative 2 by dividing it on both sides because it's being multiplied. Opposite of multiplication is division. 0 divided by anything is still just 0, so that's nice. Okay. I want to get rid of the square root sign, so I'm going to square both sides. Okay, 0 squared is still 0, so that gives me x plus 1 equals 0. So now to isolate the x, I'm going to undo PEMDAS, and I have an addition, so I need to subtract 1 on both sides. So my final answer is x equals negative 1. Okay, so that's the value that will make this thing work here. Right? So if I plug in negative 1, I will have 0, right? and this will be minus 1. And if I plug in negative 1 here, I will have 2. I'm sorry, I'll have 1. So I end up with negative 1 equals square root of 1 is 1. So we call that an extraneous solution, because even though this is what I get out when I simplified everything, that's not the actual answer that I get when I plug it in, right? So there's actually no solution in this case. Okay. So again, if I plug in negative 1, I'm going to get out negative 1 on the left and 1 on the right, which is a false statement. It's not true that negative 1 and 1 are equal, right? Because again, 0 and left with negative 1. Plug in negative 1 here, and I get square root of 1, which is 1. So x equals negative 1 is called an extraneous solution. Basically what that means is that it is an extra solution that does not work. And since there are no other solutions that do work, there is no solution for this problem. Okay, so this actually has no solution. Okay, so let's go to our next one. This is a perfect example of using opposite operations because we have some addition, some subtraction, some multiplication and division, some exponents, some parentheses going on here. We have a little bit of everything. This is the perfect example that I would like to showcase. So I would like to isolate my x. In order to get to it, I have to get to it, right? It's first being blocked by this, and then being blocked by this, and then by the exponent. So if you notice, the things that are in the way are the opposite order of PEMDAS. So first, this addition subtraction is in the way, then this multiplication division is in the way, and then this exponent is in the way, and then we can get to the parentheses, right? So I'm going in the opposite order. I'm not going from parentheses and working my way down. I'm actually starting from the end, any addition and subtraction, and then any addition, multiplication, and then any exponent. So in order to isolate this, I have to go backwards. So again, I'm using the opposite operation that's shown. This is an addition, so I have to subtract. I have to subtract it to both sides of the equal sign because I have to be equal, right? So minus 1 from here, minus 1 from here, right? Next, I'm looking for any multiplication division. I have this. So if I wanted to, since I have a fraction and an equal sign, at this step, I could have multiplied everything times the only denominator that's there, 3, and I'll get the same answer. And what that does for me is it clears out the fraction, right? This would turn into 2, this would turn into 3, this would turn into 15, and there'd be no more fractions for me to deal with. That's completely valid. There's no problems with that at all. In fact, oftentimes I'll do that as soon as I see a fraction. As soon as I see a fraction that's not inside of a parentheses, I'll just clear it out, okay? If I decide to just keep the number small and subtract the 1 and then clear out the 3, that's fine too, which is what I do here, right? So I multiplied both sides by 3, so this goes up to 12. The 3 cancels. Next, I'm going to divide, right? This is multiply, so in order to undo multiply, I divide both sides by 2. I got x minus 1 squared equals 6. So now in order to isolate the 6, I have to, so in order to isolate the x, I got to take the square root of both sides. Remember, however, though, when we take the square root, so that's me undoing the exponent. That's really me taking this exponent to another exponent, which is the reciprocal of the current one. So I'm really raising this to the exponent of the 1/2, which is the same thing as the square root. So I'm going to square root the 6. However, when I do that, I'm going to take the plus or minus of 6, okay? Because I don't know, for square root of 6, I could use two positives, right? Square root of 6 times square root of 6 will give me 6. Negative square root of 6 times negative square root of 6 will also give me a 6. So I need to take the two cases together, okay? Now the last thing I need to do to isolate this x is add 1 to both sides, and that's my answer. I want to advise you, if you don't remember, again, I'm assuming all of this is review. This is two different numbers, right? This is two answers. This is 1 plus square root of 6, and it is also 1 minus square root of 6, right? So there are two answers present here. It is not just 1, Even though it only looks like one, the plus and minus dictates that it is two separate answers. Okay. So remember, when you are working with equations, you can always check your answer, which is how we knew that this x minus 1 was an extraneous solution. Okay, I can check and see if this works for this equation, which it does. You really have to watch out for extraneous solutions when you're dealing with things like square roots, okay, or cube roots or things like that. That's when you get into issues. Okay, but we can always plug x back into the equation and figure out whether we did something wrong or not. Okay, so in theory, in this class, you can pretty much always get the right answer, right? You can always check to see if you're doing something right, right? So you should get 100% on everything because an equation can always be checked. Now, do we actually do that? Most of us don't. I hardly ever check my answers. I have other ways of finding whether or not I'm correct or not. But, you know, if I'm not certain, I definitely do, right? I check solutions all the time when I'm writing your answers. So just know you can always figure it out, right? When we're trying to solve quadratics or higher degree polynomials, we generally want to try one of the following approaches, okay? So the first approach we always want to approach with is factoring. If we have a quadratic, it is a trinomial. It's got three terms. We want to see if we can factor out GCFs, if we can use Professor Choi's method, if we can just factor in general, okay? Can we factor by grouping? Things like that. So we're going to use the property a times b equals 0. Remember, a polynomial is really just a number. And when you factor the polynomial, it's like factoring your number. 10 is the same thing as 2 times 5. So when you have your polynomial, you're breaking it down into pieces. If your polynomial is equal to 0, that means one of those pieces that you factored it to has to equal 0. So if I have two numbers being multiplied equaling 0, one of those, or both of them, have to equal 0 themselves. Okay? So what that means is, whenever I have a polynomial, I have to zero it out. Okay? I need to set it equal to 0. If it's not already equal to 0, I want to set it equal to 0. So, again, this was not a polynomial. I did not have to zero it out. It just happened to equal to 0. Here, because of the way that of its form, it was not in a polynomial form, so I did not have to zero it out either. This was a linear equation, okay? I didn't have to move everything to one side to solve, right? It was easier to solve it by clearing denominator. So it is a polynomial, it's a first degree polynomial. However, I didn't start to zero it out until the end, right? I could have had this as 3x plus 22 is 0, but I still would have had to move this over to solve for x. So linear equations, radical equations, and things that are not in a polynomial form, you're trying to isolate the x by undoing stuff, right? But when you have the special case of a polynomial, you want to try to factor it. You want to try to make it equal to 0 so that you can factor it and use this zero multiplication property. Okay, so again, when we're going through our factoring, there's a hierarchy that we want to go through. Obviously, GCF is first. Then we're looking at the terms. There's 4 terms. We want to try to factor by grouping. It doesn't always work, but most of the time it does, especially right now in the textbook. Okay. If it's 3 terms, then we look for the monic case. We look for the non-monic case where we use Professor Choi's method. Or is it quadratic in form, right? If it's quadratic in form, so what this means is it still has the form of a quadratic, a second degree polynomial, but maybe it's a 4th degree polynomial, or a 6th degree polynomial, or perhaps it is a 1 degree, and there is a square root term in the middle. Okay, so as long as it has the form of a quadratic, we can use what we call a u-substitution. A u-substitution is a very unique type of distribution, or substitution, that we use. It's very, very, very common in calculus, okay? The way that we're going to use it here It's not super common for calculus, but it's a good introduction to it. So we do have an example where we use the u-substitution. This is a very nice method compared to the way that most students would attempt the same problem. Okay. So again, quadratic in form means that the power of your a1 term is half of the size as the a2 term, meaning that the degree on your leading term is double that of the degree of the middle term, and the degree of the middle term is double that of the last term, the a0 term, the a0 term. Okay, that's what it means to be quadratic in form. Right? The last thing we can do is complete the square. Okay, so again, this should be a review as well. Although most students don't like completing the square, we will be going over it. It does come up in calculus, and it comes up in a way where you can't avoid having to actually complete the square. It's not like, oh, complete the square, I'll just do the quadratic formula. It comes up in more context than just that, right? In fact, in this class as well. So knowing how to complete the square is actually very important. It's going to come up quite a bit later on. Okay, so we're going to review that as well. Quick review right now is that if a polynomial is not factorable over the integers like we saw before, we can always find a new constant term so that it is factorable over the integers. Okay, and in fact, not only factorable, but factorable as a perfect square polynomial, right? So something that looks like this, right? An x minus 1 squared term. Okay, so that is kind of the different ways that we want to approach this. Completing the square always works for a quadratic, okay, or quadratic form. So in order to complete the square, we're going to find a new constant term. I'm going to call it a0 prime. And in order to do this, I'm going to take my middle term. I'm going to divide it by 2 times the leading coefficient. I'm going to change the sign, and I'm going to square it. That's going to be the new term that I'm going to have for my constant. And what I'm going to do is I'm going to add 0. Okay, I'm going to add 0 in a very, very unique way by adding it and then subtracting it right away, right? So some number minus itself is 0. So I'm adding in a cool 0 so that I can play around with the numbers. I talked about this a little bit in section 1.1 video, I believe, maybe the 1.2, I don't remember. But it allows me to manipulate my equation a little bit by adding this and subtracting it right away and being able to play with it. Okay. Some students have learned not to add and subtract it right away. Some students learn to add this a0 prime term to both sides of the equation, and that way you're being equal. It's really the same thing as adding it and taking it away from one side of the equation, right? So whichever one you prefer is fine, right? So either you add it and subtract it right away, or you add it to both sides of the equation being equal, okay? So either add 0 or stay equal and add it to both sides. Once you've done that, your first 3 terms can factor into a perfect square that takes this shape. So again, notice it's x minus that thing that you had here before you squared it. Okay, so just the a1 over 2a2 before you square the term. So your middle term divided by 2 times your leading term, your leading coefficient. Okay. The other way to do this is with the quadratic formula, right? So this is the quadratic formula. Again, remember that a2 is the lead coefficient, a1 is the middle coefficient, a0 is the constant term. We will talk about this again later in a form that you're more familiar with, which is the a, b, and c, right? So again, the leading coefficient, a2, would be your a. That middle coefficient would be this a1. And that constant term is the a0. That would be your c, right? So again, here we're working with the standard form of a polynomial, so I'm keeping that notation. We'll talk about it later. That transition to the a and the b and how that works, okay, the ABC. Okay, so let's go ahead and solve the following quadratic form. So we'll run into one of each of these, okay. So here, this is very simple to factor, right? I need factors of 8 that add or subtract to 6. 2 and 4 is the easiest. So we get x plus 4, x plus 2 equals 0. Now that means that one of these has to be 0 for this to equal 0, right? The only time this is equal to 0 is if x equals negative 4. The only time this is equal to 0 is if x equals negative 2. So for these ones, it's very simple. You just take the opposite value of what's in here. If it's a little bit more complicated, like 3x plus 4, just take this term and set it equal to 0. 3x plus 4 equals 0, solve for x. X plus 2 equals 0, solve for x. And then those will be your two solutions. Okay, so when there's not extra terms going on in here, it's very, very easy. It's just the opposite sign of the things that you see inside of your parentheses. Okay. Here, this is a little bit more difficult, okay, because it's not equal to 0. Yeah, we have two things being multiplied, but it's also being subtracted by 4, and I also have some term out here. So I can't just say, oh, the answer is x minus 1, x plus 3, because it kind of looks like what's going on here. It doesn't work that way. It has to be equal to 0, okay? Two things being equal, multiplied and equal to 0 means one of those things has to be equal to 0. So we have to put it into that form in order to finish solving, right? So that's a big thing in algebra, is put things into the correct form, and then you can start to apply what you know about that form, right? So if it's not in the correct form yet, we put it in that form, and then we can figure it out. So we got to zero this out. The easiest way to zero this out, because yeah, I can subtract the x and move it over. I can add the 3 and set it over, and it'll be equal to 0, but it won't be in a factored form. It won't be something times something times something times something equals 0. It'll be something times something minus a bunch of stuff equals 0, which does not look like the form I need it to be in, right? I need it to be something times something is 0. So make sure you don't mix that up, right? So I'm going to have to expand this and then move this x over and move this 3 over all at the same time, right? So this expands to x squared minus 2x minus 3. The minus 4 is still there. The minus x, and then now this is a plus 3. Luckily, this 3 and this 3 cancels, so I know my constant will be negative 4. This x and this x combines, and I'll have a minus 3x, okay? So now I am in a form that I'm familiar with because it looks like what was going on in A. So now I say, okay, now it's a standard polynomial. I can factor it. Factors of 4 that add or subtract to negative 3, negative 4, and a positive 3. Or positive 1, sorry. So then my answers are x equals 4, x equals negative 1. So see, we have x squared plus 4x squared minus 2 times x squared plus 4x minus 15. Now, most students, when they see this, the number one thing that they do is they expand everything. They get negative 2x squared minus 8x minus 15, and then they use the special product here. And if you notice, what that does is you square this, you times 2 and multiply these, and then you square this, right? Remember, we're squaring. It doesn't just square both terms, right? So when you multiply this out using the special product, you're going to end up with a 4th degree polynomial, okay? We have not gone over how to work with 4th degree polynomials. A 4th degree polynomial doesn't have only 4 terms. This one would have only 4 terms, but I believe separating by grouping still doesn't work for this case. Notice that it is quadratic in form. The first thing is squared. The next term is identical, right? The variable part, this quantity that I have, and it is not squared. And then the last term does not have that quantity at all. Let's say I replace this with u. Let's say I said u equals x squared plus 4x. Okay. Then this will look like u squared minus 2u minus 15. That is way easier to solve than trying to expand this out because this is factorable, right? This factors to u minus 5, u plus 3. Right? So what that tells me then is that u is 5 and u is negative 3. But we're not done, okay? Because I don't give a shit about u. I'm talking about x, right? So I need to take my u and resubstitute what the value of u is. U is x squared and 4x. So I need to bring that back into the world of x and out of the world of u. So I just make that substitution. U equals 5 means that I have x squared plus 4x equals 5. U equals negative 3 means I have x squared plus 4x equals negative 3. I cannot solve either of these problems as they stand. They almost look like trinomials, right? I need to put them into a standard polynomial form. So I'm going to subtract 5 and I'm going to add 3. I'm going to zero out both of these equations. Now I can factor, okay? In order to get this to work, I need a x plus 5, x minus 1. In order to get this to work, I need a x plus 3, x plus 1. Right? And then those are my answers. My solutions to this original equation are x minus 1, x equals minus 1, x equals minus 3, x equals 1, and x equals minus 5. There are 4 solutions here. Okay? You would not have been able to get that the same way. Maybe you would have if you expanded this. Okay? It probably would have expanded to give you a x squared minus 1 somewhere, common factor. Right? But it's much easier to do this with the u-substitution. This is especially difficult if this does not factor by grouping well. I believe if you expanded this out, you probably still could have did a factor by grouping. But what if we ended up with answers that were not whole numbers? Like minus square root 3 and a positive square root 3. This would be much messier and it would not work by factor by grouping. Okay. So next we have x squared minus 3x minus 5. There are no factors of 5 that I can use to add and subtract to find a negative 3. Factors of 5 are just 1 and 5. There's no way to get to negative 3. So this is prime over the integers. It's non-factorable for our cases. So since it's non-factorable, we need to do one of two things. We either need to complete the square or we need to use the quadratic formula. Okay? Those are the only two things that we can use when I cannot factor something out into their pieces in order to find its zeros. Okay? So it's not factorable, so we need to complete the square. My new constant that I'm going to need is the middle term divided by 2 times the first term, so 2 times 1, negative. So this is really a positive 3/2, okay? And I need to square it, so I'm going to get 9 over 4. And I'm either going to add that to both sides of the equation, or I'm going to add and subtract it right in between the second and third term, okay? So I'm going to be nice, and I'm going to add it to both sides, right? So when I do this, I also need to move this 5 over, because again, this constant term of negative 5 is the thing that's giving me a problem. It's the thing that's not allowing me to solve this. If this was a different number, like negative 4, for instance, then I could factor this. It would be no problem, right? But since the factors of 5 don't combine to negative 3, this is the guy that's giving me issues, right? So I'm going to move it to the other side of the equal sign, as well as add my new constant that I need to both sides. So basically, this thing is getting replaced by 9/4. So I get rid of it, but I'm still not changing the equality by adding 9 over 4 to both sides. Okay, so this is the new polynomial that I'm interested in. Okay, it actually factors to a perfect square, and then this I'm just going to add together and combine it, right? So this is going to be 20 over 4 plus 9 over 4, so this will turn into a 29 over 4. Here, this is going to factor to be x minus, and then what this was before I square it, so 3 over 2. So this factors to x minus 3/2 squared, okay, like so, x minus that whole thing before I squared it, and then I'm squaring the whole thing. Okay. So x minus 3/2 squared. So that's the perfect square form of this. And this I just combined together. Do not try to clear denominators here because we are not solving it yet. We are still in the process of putting it into a familiar form so that we can solve it. Okay. Actually, as it is now, this is my familiar form. From here, I can solve, right? So now, if I want to start to solve this thing, I can start to isolate x, right? I can take the square root of both sides to get rid of this 2. So that means I get x minus 3/2 plus or minus 29 over 4, just like we did for this example we had right here. Okay. All right. I have it pretty much in this form here. Actually, we'll say in this form. Something squared equals a number. So it's time to square root both sides. And then I will take whatever I have on the inside and move it to the other side. Right. So that's where we're at. Okay. So here, I can now isolate x by undoing the square on both sides. Okay. So I have plus or minus the square root of 29 over 4. The square root of 29 over 4 simplifies to plus or minus 1/2 times square root of 29, because 4 is a perfect square. So it stays in the denominator position. I can pull it out as a 1/2. And then I just have the square root of 29. Okay, so I have my non-radical part on the outside, my radical part on the inside, my plus or minus. The next thing I need to do is add this 3/2 to the other side so that I can isolate my x, and I've solved my problem. Okay, so I completed my square. If you notice, it really didn't take that many steps in order to do this. Even though we have not nice numbers, there's still a bunch of fractions going on. It wasn't a whole lot of work. Okay, so once you get it into this perfect square form, it's just like that example we have. We can start to square root both sides and then just move over the piece on the inside. Now, I could have also used the quadratic formula. That's what the quadratic formula is for. It's derived from completing the square. Okay. If I plug in all of the pieces, again, this is that b term, right? That a1 term. 1 is that a2 term, and -5 is that a0 term. I just plug everything in. That gives me 3 here, right? Because you use the opposite value of the middle term, the middle coefficient. 2 times the lead coefficient. That middle coefficient squared minus 4 times the lead times the constant. So this is going to give me 9 plus 20, or 29. All right. All right. I guess it in 2 parts. Okay. And then I can take this thing and I can separate it into its 2 pieces. Right. So when I do that, this 2, when it attaches to the 3/2, it doesn't just disappear because it's also dividing 29 in half. Right. So when I separate this from a single fraction into its components, it's the same exact answer. Okay. So let's go ahead and complete the square on a general quadratic equation. So a general quadratic equation will have a leading coefficient of a middle coefficient of b, and a constant term of c. Okay. We could keep it as a2, a1, and a0, but I know that's confusing for people. So we're going to use the standard notation that we generally have. So for a general quadratic, we have a, b, and c going on. Okay, so we're going to complete the square on a general quadratic equation, right? That's set to 0, right? So what we can do is to get rid of the a term, which is especially nice since it's equal to 0, is divide everything by a. Now, if this term was non-zero, well, we would just add it to this constant and divide it by a anyway. So it really doesn't matter. Okay, so here we now have a polynomial that is monic. And just because these look like fractions doesn't mean that they actually are fractions. It's very possible that b and c are both multiples of a, right? Maybe there was a common term here, common factor. And so these can still be whole numbers, right? So maybe this was 4 and this was 2 and this was also 2. That makes this 2 and that makes this 1, right? So these can still be whole numbers, but the form that they take from the general form of a quadratic equation will look like this. So this is what we're going to use to complete the square. So we know we need to take we need a new c, right? This is the value that's not working for us. So we need to replace it. We need to move this to the other side, and we need to replace it with a value that is this number, b over a, divided by 2 times what was this number, which is mnemonic now, so nothing. So b over a, that value over 2, and we're going to make it negative. We're going to change the value of it. We square it and we add it to both sides. Okay, so again, that's coming from here, right? The middle term divided by 2 times the first term, which in our case is 1, and we square it after we change the sign, and we add that to both sides, or we add it and subtract it. Okay. There we go. Right? So first things first, let's move this to the other side because we don't want it around. It doesn't help us out. It's actually detrimental to what we need to do. Our goal is to replace it. So we move this to the other side of the equation. It becomes negative. I find my new term, okay, which is b squared over 4a squared. Because remember, I had b over a over 2. And I'm going to end up squaring it. So b over a divided by 2 gives me b over 2a. b over 2a squared gives me b squared over 2 squared is 4. A squared is a squared. So I'm going to add that to both sides of the equal sign. Okay. So if you notice, I added to the far right of the left side equation and to the far right of the right side equation, just so that I'm being extra equal. Okay. Now, I can combine this by making a common denominator, right? So I have an a, I have a 4a squared, so this already has an a, but what this does not have is a 4 or that second a. So top and bottom here, I would need to multiply times 4a, giving me a common denominator of 4a squared and a 4ac on top. This factors into a perfect square, right? And the perfect square form is going to be x minus b over 2a. Okay. So x minus a minus b over 2a makes it positive. We also know it's going to be positive because look, positive and positive. If there was a negative here, one of these signs would need to be negative. So that also helps me to figure out what sign I need to use. So I know that this is positive because everything else here is positive. If we go back to what we had here, when we had this perfect square going on, notice we had a positive and a negative going on. So our perfect square form needs to have a negative on the inside. Okay, so that's another way just to quick check to make sure your signs are correct. Okay, so I have my b over 2a squared. Here I made my common denominator, so I can add them now. I can have negative 4ac plus b squared over 4a squared, or I can switch the order to what we're used to, which is b squared minus 4ac. Okay, so that's what I did here. I just combined them. The negative 4ac was the negative term, the b squared was a positive term. They're still positive and negative respectively. So from here, we're in that same situation. I'm trying to isolate the x, so I can start to do that now. I can square root both sides. Okay. Notice that this is a perfect square. 4a squared is 2a. So I can square root the top and square root the bottom because that's a property of the square root sign. So I can pull this now out as a fraction. The square root of 4a squared is 2a. Okay, so I still have 2a on bottom. This is plus or minus because when you take the square root, you don't know if it's the dual pluses or the dual minuses to get your value you just squared. If I want to isolate the x, I'm going to subtract the b over 2a to both sides. And that's my quadratic form. Okay, so generally when we see this, we write it all over the common denominator. Although I do prefer you to separate your answers into 2 separate terms, right? Your term with the root and your term without the root. But the general form is to have this over the same common denominator. Okay, and that's where the quadratic formula comes from. So again, when solving equations, we always need to check our solutions because we may have extraneous solutions, right? Those are solutions that don't actually work for our equation, as we saw in that example before. Okay, guys, I'll see you on the next video. Thank you.